Okay, cool. So I think we are live. Yes, we are live. Um, cool. So what is it that I'm intending on doing today? So the thing I want to do today is I know for the what I want to do today is just run through quickly the analog to digital converter on the Cortex M4, and for that we'll be using STM32F47 MCU. Um, the objectives of today are quite simple. So I think let's actually write out our objectives here as comments. So configure ADC, configure ADC. So we accept input, one input, one input on one channel, and then read input and print it, and then do floating point arithmetic on input, print the above. It's going to be really simple to do this, and I'm hoping I can run you through it really quickly. I don't want to make another uh, I don't mind doing them, but I want to make today's stream super short, 30 minutes, 40 minutes. You're back to doing what you were doing before. I'm back to doing what I was doing before, even though it was it was most likely probably streaming before. So this is four objectives for today. Configure ADC, read an input, print it, do floating point arithmetic on this on said input, or on said reading of input, and then print that. It's very simple. Like this should take us very little time. So let's quickly understand the concepts that we have to go through, and then go from there. So okay, cool. So what is the analog to digital converter? So the STM32F4 family, which is the 407 that I'm using, has a 12-bit. Uh, it has a up to 12-bit successive approximation analog to digital converter. So basically, it samples the signal that's coming in using the Nyquist theorem at a fast enough speed that you get over 2. Okay, cool. So it has up to 19 multiplex channels, allowing it to measure signals from 16 external sources and 2 internal sources, plus the VBAT channel. So plus the VBAT channel. So that's 16 plus 2, 18, and then plus VBAT, um, 19 multiplex inputs. So I think today we're going to use one of these internal inputs, although the change from using an internal input to an external input isn't that big. You just need to choose a different channel number, and you need to choose when you do choose a different channel number, you'll have to set up that port port pin. Basically, you're going to use some port pin as an ADC channel. So you'll have to set that port pin as an input, as an analog input, and then you can read from there. And then also be sensitive of like 5-volt and 3-volt pins and such. So cool. So 2 internal sources, feedback channel, and AD conversion. So today we're going to use the 12-bit resolution. We won't use interrupts today. we'll use a single conversion mode. So basically, we'll just read one thing. We won't use scan mode, but this is eventually we can add scan mode. If we needed inputs from 2 or 3 different channels, we could use scan mode. But today we're not going to use scan mode, so we just read one. Data alignment, cool. Think we'll use right with data aligned, and then programming sampling time. That's fine. We can use it. We can program the sample time for each channel. We'll get to this probably, and then we have an external trigger option, so we can get interrupts from XDI and use those. And then there's dual and triple mode, and we can configure DMA, but we won't use all of this. And then, of course, obviously, these are the supplies and requirements for our ADC at the moment. Okay, cool. So let's now, I think, let's kind of find out. Yeah, so that's the ADC block diagram. What we're basically going to do today is use one of the internal ADC 1 to 15 on GPIO ports, and then we have the temperature sensor, the VREF int and VBAT int. So since we have a temperature sensor on board, we're going to use the temperature sensor, which comes in. It could be either in a regular or an injected channel, and then it goes through the regular converter. The regular will be using regular channels. It'll go to regular data register and we'll read it from there. And then obviously we have interrupts if we do need interrupts and want to use the NVIC for those interrupts. But for now we won't be using them, so that's fine. To keep this as simple as possible. Cool. So what are we intending for today? We need to read the temperature sensor through a regular channel, and then from that we need to go to the ADC data register and collect the stuff that we've read. Cool. This actually makes it. Is it just me, or the more I do embedded work, the more block diagrams become very friendly, and you can almost write code from block diagrams? They used to be quite scary. And I mean, the more you look at them, but it's about looking at the block diagram in context and practicing what you're looking at. So a lot of this is about like repeating something quite a few times before you're confident enough in just before you you will have you will have to do the thing that you're scared of before you get the confidence to do the thing that you're scared of. Doing the thing that you're scared of will give you the confidence to do the thing that you're scared of. It's quite, it's a silly one. Cool. So, but that's what you're going to do. We're going to use some ADC, run through channel, I think this is ADC 16 here, ADC 1 to 5, so it's 16, 17, 18. So from 0, that's 19 channels. And then take it through a regular channel, and from the regular channel, read it out. That's really it. It's going to be that simple. So what do we need to do? So let's go. These are basically some important stuff, some important notes if we need. So the VREF, VDDA, all these are reference voltages that they're reference voltages that your ADC needs. So the way the ADC works is that it has an internal analog to digital converter. The internal analog to digital converter will sample voltages until they're equal to what the ADC is reading from the input, and then when we do get the voltage equal to what it's reading from the input, this is what we will be told. So this is the resulting data that we'll have. Okay, cool. So let's look at some more stuff. So we power the ADC by setting ADC on bit in CR2. So that's how we do. And then we do conversions by do SW start or JW start in JW start, I think they are in CR1 or CR2. Uh, JW start, JW start is going to be in CR2. So let's set this speed is set by SW start conversion of regular standard channels set by software. We can start. So let's look at JW start conversion of injected channels, blah blah blah. So cool, awesome. We were at the functional description, I think. Yeah, functional description. So here we were, and then we looked at the clock. So the ADC has a couple of clocks, and the clocks are used for obviously setting a good sampling rate so that you can read your data correct at a good speed, at a good enough, at a speed that covers you for the Nyquist sampling thing theorem. Nothing. It's just you will encounter it. It's in your statistics course. If you're doing a course, if you're not doing a course, then just look into digital signal processing statistics, and you'll find out why quite a lot of this is coming from there. What you need. Okay, cool. So channel selection. There are 16 multiplex channel, ADC 0 to 15. And then we obviously have the temperature sensor VREF int in that. So cool. So for this STM32 F47, this is the one we're using it. The temperature is pushed into ADC1, input channel 16. And then we have VREF int, it's used to input channel 17. Okay, cool. And for single conversion mode, we need to set this in the ADC register. If we need single conversion mode, does one conversion. This conversion is started with the cont bit at 0. So cont bit at 0 is going to be the cont bit at 0 is probably going to be, I think it's in the let's look at it. Going to be either in CR or in CR2, CR or CR2. Okay, let's do CR2. Let's look for that cont bit. Okay, cool. Continuous conversion. This is single conversion, single conversion one. Cool. So this is anyways the default one. So we want one single conversion. Cool. So we have that. We know where we know where to find that. So single conversion mode. So it defaults to single conversion mode, and then we need to start the reading by DCCR1, and then we probably need to set, before we do this, we need to set resolution. So let's look at CR1. We need to set a resolution. By default, it's on the 12-bit resolution. You can leave it. We can leave it as that. This actually makes it a lot easier for us to use. Okay, so we might as well forgo this just because we don't need to set it right now. Okay, cool. It makes the code a lot simpler. Cool. So we need to, okay, I think I'll let's do code as we let us write comments in our code as we do that. So configure here, we'll need to first of all enable clock. Okay, and then we need to choose resolution we've seen just now, and then we need to set conversion mode, which is single by default. Single default. Okay, so actually let's put in this code. So we RCC put APB1 APB2 ENR, and then let's set it as let's set the ADC1 bit. So let's set 1, let's set it to RCC APB2 pb2 pb2 no, I'm wrong. pb2 I need a macro, and then adc1 pause. Okay, so let's enable adc1. Cool. Let's choose a resolution. Um, let's choose a resolution. We know we want to choose a resolution. This is so that so if we do nothing, we can set set resolution bits to 00. And the way we can do that is by just let's clear those bits. Yeah, just we could do nothing. It still works. And this one dot cr1 dot cr1 1, and let's just reset them so that we have some clear data there, just so we have something to do. But this is not entirely necessary since mm, uh, pause, pause. This is not entirely necessary because choose 12 enable clock, choose 12-bit resolution, enable ADC1 clock, and choose 12-bit resolution. This isn't entirely necessary because it's already on single mode. I mean, it's already on 12-bit conversion. So this is this one as well. So we don't need to do anything here. If we want, we could reset that. We could reset this count bit. Where's the count bit? Where is the count bit? It's somewhere here. If we want, we could reset this count bit, but it is already reset. Okay, so we could go like, okay, ADC. Okay, which one? Sorry, ADC ADC1. This is CR2. ADC1 dot CR2 to and equal. Oof, oof. Oh, let me know there. Let me start comments. Docs, chat, and we are live. Okay, cool. So just running comments in case someone sees something I'm doing wrong and can help me. So that would have been disastrous there. And then what we have here is ADC1, ADC, CR2, count pause. Perfect. So we made it single conversion. Okay. So what other stuff? What other stuff do we need to set up? So we need to set which channel we need to read, and which channel we need to read. We need to set the reading channel, and this is going to be set from watching the time here so that we can go. I think it's this one, sequence register. So we need to set our channel number. Okay, and we're going to use, so this is, we need the fast conversion because we're only doing one regular conversion. So we need to set that this we need to set this fast conversion in regular sequence. So we need to set which channel. Do I make sense? Which channel to be read fast in the regular conversion. Cool. So let's set channel number 16. Which channel? Set channel to be read. So let's clear ADC1 dot sqr3, and then let's clear it so before we can set it, so we can set it to like a sanish 0 cross 1f. So y1f, so we clear y1f, so we clear the first 5 bits. Okay, then unit 32 underscore t channel number equals 16. That's the scene 16, and then we need to do ADC DC1 dot SQR3 dot SQR3. Okay, cool. Is equals. So let's channel. So let's use the mask we used earlier to set channel number 16. So we've set the channel to read. We're reading channel to be read. ADC1 in 16. Okay, cool. So we have that. And we'll set that later. Okay, cool. So now let's do our sample rate. Okay. So let's look at which form which what does sample rate do? So sample time register. Uh, These bits are written by software to select the sampling time individually for each channel during sampling cycle, the channel selection. So we need to set how many cycles between samples. That way we can, you need to read it fast enough so that you can convert it. So let's set it to this. Let's set it to 480 So our sample rate. Understanding ADC sample rate. So what is the ADC sample? The ADC sample rate refers to the number of samples per second. Okay, cool. So we want for 80 samples per second. So that's kind of the speed at which we are sampling. So, okay, cool. So let's change that sample rate. So ADC1 dot SMPR1, then 7 ADCSMPR1 SMP 16 pause. Okay, cool. So let me quickly go back there and show you why we did that. So SMPX, okay, channel X sampling selection time. So our SMPR1 has channel 10, channel 11, channel 12, channel 13, although it's channel 18, okay? And then obviously SMPR2 has channel O, although it's channel 9. Okay, cool. So you can get those. That's what I'm doing here. So I'm setting channel 16 sampling time. Perfect. 16 bars. And then let's do so in order to read the temperature. So reading the temperature sensor. The TSVREFE, which is the internal the internal reference voltage. TSVRV. I think it's in CCR, the ADC CCR register. So this is the ADC common control register. Temperature sensor and VREF int enable. This bit is set and cleared by software to enable and disable the temperature sensor of VREF int. Okay, so Basically, uh, we need to enable this bit so that the temperature sensor can go on and so that we can use it. Okay, cool. So we need to use the ADC common, ADC common, ADC common temp sensor. Okay, ADC CCR. Okay, and then what do we need to do here? This is one. Okay, start ADC. ADC CCR. Sorry, I go into thinking. R, and then we want to do TS VRFE pose. Okay, cool. So that's it. And then we need to, after that, we need to do, what do we need to do here? We need to start ADC1. Okay, cool. So ADC1 dot CR2. We saw this. We saw this in the reference manual coming. CR2, and then we have an on. I think it's the 0th bit, ADC converter on and off. Okay, cool. So let's set that ADC converters on. Cool. So there you go. ADC CRR2 Edion pulse. So what have we done? We've walked through this, and basically what we have here is we have configured ADC so that we can accept input on one channel, and we've done all the relevant little bits so that we get the correct speed, we get the correct channel. We're measuring the correct channel, and this channel number is internally connected to the temperature sensor. But if you are doing like channel 0 or something, and then you needed it to be on port B0, you would need to enable port B, and you need to set port B pin 0 to analog input. So remember, in our document, it mentions that our temperature sensor has a ramp up time. So there is a ramp up time. Yeah, there is a ramp up time. Yeah. Okay. The ADC also, the sensor has a startup time after waking up from power mode to power down mode before it can output at VSense, and the ADC also has a startup time. So let's add, I have a really stupid formula, a really stupid function up here, which is busy wait. Let's do a little busy wait here. So give ADC and temp sensor time to ramp up. Okay, so let's run a delay here. Perfect. Now let's try and read the data. How do we read data from the input? So what we need to do to read data, if you found a start bit. This start the conversion of the regular channels. Okay, so remember we're doing regular channels and not injected channels. So let's start the conversion on ADC1, CR2. CR2, let's start the conversion, and 30, perfect. Okay, so let's start the conversion, and we say 1, and then we boom, boom, and then we set ADC CR2 SW start pose. Cool, so we start the conversion there, and then let's wait, let's look at the status register before we go on, so you're not confused. I've jumped through all these registers, there's many. So one of the things I do when preparing for this streams both for myself and also all the other presentations I make online, is I jump through the documentation enough, and I would go through and read this through this peripheral description in full and write a driver. But that makes my videos quite long, and I want to see if I can avoid that. So I want to do all the prep work before, and then I can do it here. But if you guys want to see, if you guys want to see me do this live, I can do it. So end of conversion. We have regular channel end of conversion. So we need to do one thing. So number one, start the conversion, and then we need to watch. We need to wait for a flag to be set that it's been set. So while not, so while this flag is not set, adc1 dot sr, okay, and let's say, let's put a mask there, one, and okay, let's do that, and then adc sr eoc pose. So we're waiting for this flag. Wait for end of conversion. Okay, cool. And then once we get internal, wait for end of conversion. Now we have our conversion, we can read it. So read ADC row input. Okay, so we have ADC temp row. So so temp temperature row date. So this is, say, assigned int 16, I would say. Let's make it uint 16 underscore t. It's gonna become signed at some later point, and then let's go here and say adc dc1 dot 1 dot dr data register. So we can look at this one as well, but from the naming of it, we know what it is. ADC1. So reserved regular data. This contains a conversion for a result from regular channels. Okay, so cool. We're getting we're choosing what has been read from that one. Okay, and then let's first of all see if we get any values here. So to see if we actually do get print, so let's do printf some values from ADC conversion. And then we need temperature row. Okay, cool. And then I want to probably set a, let's add something here, delay. I want to set a breakpoint here so that I can just debug my code and run it through there. Okay, perfect. So, slight recap. We've done all of this. We've configured ADC, and then we've set the channel to read, and then we've set the sampling rate. And then here we started, we give it a delay to ramp up. We start the ADC, we start the temperature sensor, and then we give them time to ramp up, and then we start the reading, wait for the reading to be done, and look at that conversion. So let's debug this. This should work. It's okay. It's okay. syntax error. Is that it? Is that all I did need to do? Sorry. That's code from something else that's affecting us. So you int 32. Build this. We still have two warnings. We still have two warnings, but it's okay for now. So let's look at the SWV data console. And I think I've already set that up so that it's getting all the data. And then, okay, cool. So I want to now bring this out and let's walk through this line step by step. I mean, we can also observe our SFRs and see what they're doing, but we'll get to that later. So let's just walk through this. No, we can. There's no need to. This is all, you can do this by yourself. Okay, cool. So let's, system booted with default clock. Obviously, you cannot see that. No, not there. So I know you can't see all of this down here, but this basically, can I zoom? I'll copy the stuff up there and post it. So system booted with default clock, and then let's see if we get some logs. Okay, cool. So this is what we get so far. When I copy that and I put it here, this is what we get. System booted with default clock, system value for ADC conversion. Boom. Wow, we have a value. So we have some sort of value. Okay, cool. So let's try and convert this value that we got into some meaningful data. Now, the first thing we need to do in order for us to convert this value, we can just do it all. Okay, so let me just read it up. So reading temperature sensor. So reading the temperature sensor. Cool. We have a range from -40 to 25. That's fine. So how do we read it? Cool. Cool. See. So read the resulting Vsense. Vsense is going to be the voltage. So Vsense is going to be some voltage at this. The first thing we need to do is convert raw data into voltage. I'm just going to use Google to show you this because I think it's much easier. STM32F47 convert raw ADC to voltage. Okay, so when we get a voltage measurement, there's a formula we need to use because so this is the formula. ADC reading over 4095 times VREF. VREF is, we have all of this data. So all of this is, it will tell us to go and look at VREF. This will tell us to look at the data sheet. Yeah, we need to look at the data sheet, which is this one. So we have I think we have VREF. VREF. What? Okay, cool. So it's VREF pin. I'm trying to find VREF. Okay, cool. Here it is. So it has a typical one. Okay, typical of 1.8. And but it comes to, I think it goes to all the way to 3.3 and such. And basically, what I want to explain here is that we want to do this calculation using how do I say it? We want to take the ADC reading and then make it so our VREF, I'm going to assume it's 3.3. Okay. um VREF is, so assuming the SSA is not zero, is at zero, and VREF is at 2 point, then you should use that. So we need to find our VREF, but our VREF plus is going to be something like, in typical max VDDA. So VDDA, we need to find VDDA because this is going to be VDDA is going to be the one we're going to use. Okay, so it's 1.8 to 3.6. We're going to use 3.6. Why are we using 3.6? This is because when you're using VREF, it's easier to just do the, if you use your max value, then you've covered for all of the, for all of the, basically, for all of the uh, ranges. Yes, ranges is the word I was looking for. So let's jump into that one. Ah, there's a problem. Cool. This is what I was talking about. So in order for you to do, so we found ourselves, look, we found ourselves, basically what has happened, basically what has happened is we found ourselves in a point where we need to do um, floating point arithmetic. Okay, the STM32F47 does come with a floating point unit. So this is, I expect this is the data sheet. It's fine. It's fine. We can still use the data sheet. So let's look at the table of contents, introduction, and we see ARM. Cool. I just need a description. Yeah. So RISC core coming almost to 168 megahertz Cortex M4 core features a floating point unit single precision. So we need to enable this floating point unit so that we can actually um, do floating point arithmetic. There's a few steps to this. Okay, in order to enable this floating point unit, we need to look at this is all going to be in the ARM side of life. So we need to look at the ARM documentation. Come on, show me. Where do ARM documentation? We need to go ARM programming manual, and then we need to find FPU. Let's find it. So this is too low. I just want to go to where it's fast mentioned. This is too low. This is going too low. I want to go to page 34. So let's see. Optional floating point extension. So if it comes with a floating point unit, you need to enable it. And so basically, yeah, it comes with one. We need to enable it. And in order to enable it, I'm looking for the instructions. I do know where the instructions are. I just want to show an example of finding them. That way, FPU. Here's the thing. I know where to find them. So here we want to go to the SCB block, SCB registers. So we have SCB registers, SCB register. Okay, cool. SCB. yeah, system control here, and here's CPAR. Cool. Let's go here. Co-processor access control. So here we have this CPAR specifies access privileges for co-processors if a co-processor is not implemented. Cool. So, but what we need to do here, what we know here is we want the CP10 and CP11. CP10 and CP11 are for the enabling access to the floating point unit. Okay, cool. Enabling access to the floating point unit, you need to touch CP10 and CP11, and basically you need to enable them. Okay. So we need to write binary 1 to those to CP10 and CP11 to enable the floating point. That's number one, the first setting we need to do. So let's CMSIS does give us this utilities. So let's enable the FPU. You can do this anywhere in code. It's quite interesting. Okay, cool. So enable the FPU. SCB, CPSER, we basically change to CPSER 10 and 11. Okay, so now we have a floating point enabled, but this does not fix everything for us, because what happens now is that if I stop this, we need to make sure our compiler, so let's look at our compiler. Our compiler includes includes sorry, yeah, so linker. We need to make sure our linker includes these flags here. Okay, I think compiler something like, I think it was in general, maybe linker general, libraries, miscellaneous general linker. Okay, cool. I'll show you the flags themselves. So the flags we need is MFPU, that, okay, the floating point unit, and this one, and then you need, optionally, you need these. So these are the flags you need. I'll put them here so that you can read them. So you need FP floating point version and all of that, and then you need a mfloat, and then you need a mthumb, and then you need you print float and you scan float if you want to do print and scan of floats. So we've enabled the FPU here. So let's now proceed to do, let's convert that reading. You see the raw data here to, so let's make it float temp voltage. Now we can make it a voltage equals to float, and then actually cast what we had before into a float, temperature rho, and then we need to do that over 4096 and then times 3.3. Okay, and then we can do the same thing here, and then let's just printf adc rho value to voltage from a DC conversion, temperature rho. Let's do temp voltage. Okay, perfect. So let's do that. Let's do that, and I think we have a breaker there. So let's remove this guy, and then let's put this. Let's add a breakpoint here. Okay, and then I'm gonna go to my SWM, my data console, and I'm just gonna do play. Okay. That did not end up the way I wanted it to, but let's see. Oh, I know what the problem is. So temp voltage, this should be 1.1. So WM to the console. You can play that. Ah, conversion, ADC conversion. Cool, perfect. Let's see what we get. Where's this? Okay, so this is what we get. Let's read this. Let's read. I'm gonna stop the debugger so that we can read this. Okay, so we get ADC 0.08. So we have a voltage value. Once we have a VSense value. So let's call this VSense. Actually, VSense. Okay, and then let's call it VSense. VSense. Okay, cool. So now that we have all this, we can go back to our reference manual and then temp temp temperature sensor. Cool. Fine. And we want to go to reading the temperature sensor. So we have a V-sense now. Amazing. So if we have a V-sense, we can do this. We can do all of this. Let's do it. And where do we get this data? We get it from our data sheet. Where's our data sheet? Data sheet is gonna be here. VSense V25. Okay, cool. So here you go. We have it. We have all the data we need. V25 0.76. So we need to do that. So we need to do. It was VDEG. VDEG. Okay. So float degrees. So let's make this into degrees. So we want to do, I think it's voltage, VSense, VSense minus 0.76. Okay, minus 0.76. And then I know we need to do, here it is, minus 0.26 over average slope. So what is average slope? Over average slope. Our average slope is 2.5. Oh, wait. Remember? Look, this is millivolts. So we need to make it milli. Okay. So let's do that. 0.25 because one is, so this is going to be like 0.25 and then here we're going to do plus 25. This is just described as a, this is just described here. I think in the document it's just 25 plus 25. Okay, because we basically we convert everything to what it would be at the 25 degrees Celsius and then we adjust it for that. And then now we want to come back. And after we come back, let's do this and then let's do VTEG. Oh, I'm hoping for this one to be so short and we actually get what we want. It's going to be amazing. So let's say raw voltage from ADC to temp in degrees Celsius VTEG. And then we obviously have a breakpoint there, and then we can do save, and then we can do that. And let's look at the result we get. SWV. Let's run it until it stops. Boom. Okay, cool. So let's stop this, obviously. And I'm going to come in here and I'm going to paste this. Oh, Zach, oh Zach, why would you do that? Why would you do that? And let's debug one last time, and then we spend 15 minutes just going through this again because perfect. Okay, so this is the logs that we now get. System booted with default clock of 16 megahertz. Some values, some value from ADC conversion. So this could be raw values from ADC conversion. Okay, cool. Raw value to voltage from ADC conversion. We have a 0 millivoltage here. Raw voltage from ADC in temp 2 degrees Celsius. Boom. And our little processor is running at our little processor's voltage is running at 25.2 degrees Celsius. So again, um, I think let's go back to let's do a quick code review and we're done. Okay. So again, um, from today, what have we done? So we went through the steps to basically enable configure the ADC, and then after we configured the ADC, we basically measured a value from it. And once you measured the value from it, we went through floating point arithmetic backwards and converted the value into a human readable value that we can use. And basically what we've ended up doing is we've ended up using we know how to use the ADC now. We know how to use the floating point unit now, and we can use both of them to make meaningful data out of raw sensor values from from everything else. Yeah, I really tried to make today's one really short. I really tried to make sure that I'm really glad it came out at an hour, and it came out at an hour, and we managed to complete everything that we had set out to do. And I'm really happy for this. And thank you so much, everyone. Thank you for coming. Thank you for watching. And in case you learned anything or you didn't learn anything, if I was unclear or some sort of issue there, let me know. Please comment and like, and cheers. See you tomorrow. I don't know what I'll be doing then. Amazing.